Okay, the next one I'm doing here is 4.58. This is also another very simple problem. This one is, honestly, I think they just came up with it just to practice the material derivative. In this particular case, it gives you a function for this temperature of the exhaust in an exhaust pipe. We can see that the temperature is a function of time, and because it has a t here, and it is also a function of position. This is going to be interesting. We have some constants here that we're just going to plug right back into here. I suppose they gave them separately just to help you keep a little control over it. If the exhaust speed is a constant 3 meters per second, that is, our velocity is 3 meters per second in some direction. If you consider an exhaust, it really only goes one particular direction. Even if the car, if we have like a car, and here's the exhaust pipe, then even though it may be coming out at an angle or whatever, it's all pretty much along one line. So we're going to call this line X. This is our x-axis. Everything's going to happen along this axis. So when they give us a velocity, it's along the x-axis unless it states otherwise, which it does not. Determine the time rate of change of temperature of the fluid particles at x equals 0 and x equals 4 when t equals 0. Again, I put a lowercase d just so that I can make a point that this is actually not exactly correct. If we're looking at the particle, then we want the material derivative. Let's go back to black so I don't alarm people too much. Alright, the shorthand way of writing out this equation is dt partial derivative with respect to t times dang it, I forgot what that function was. Times the gradient, that's right. Times the velocity, plus the velocity times the gradient of t. The gradient, the way I understand it, is basically a way of taking a scalar and making it into a vector. Alright, and if we care to expand this, well, we have temperature is now a function of time, so we can take a partial derivative with respect to time, and it will not be 0. Or at least not necessarily. I don't know. We might get really lucky and everything cancel out, but we can't just assume that. Alright, we don't even have to look at the the gradient of t, though if we did, we would see that there are no y's or z's in here. So if we were to take the derivative of, which is basically the gradient is the partial derivative of each section, if we were to take the partial derivative with respect to y or with respect to z, it would be 0. We can also look at the velocity. Its y component will be multiplied times the derivative of the temperature with respect to y, and its z will connect with the derivative of the temperature with respect to z because of this dot product. And both of those are 0. So we're not going to have anything except dt, or that's not right. We're not going to have anything except u times dt with respect to x. Alright, we can start solving this. Let's take the derivative of t with respect to time. Okay, we don't have any time in this function, so we can just treat that as a constant. In this section we got 1, which goes to 0. And then we've got c cosine omega w, which if we take the derivative of that, it is negative cw sine omega t. Plus u, which is simply 3, times the derivative of t with respect to x. Alright, this time we are going to look at the first part of the equation because that's where x is. The 1 goes to be 0. The a, e, to the negative b times x. The negative b will come down because of the chain rule, so we have negative a b e to the negative b x times, let's see if we can fit this in here, 1 plus the cosine omega t. Now if both sets of parentheses here, both this section and this section, had t's and x's in it, we would have to do the chain rule in order to work this out. But if we did do the chain rule and took the derivative of this second section with respect to x, it would just go to 0 because there's no x's in there. Alright, in both of these cases, x equals 0 meters and x equals 4 meters, we're looking at the time equals 0. This is our friend. Whenever you see sines and cosines and you get zeros, they are your friend. They help you get rid of stuff without actually having to solve it. This is a sine of 0. This is the way I always like to think of it, is with the unit circle thing. Sine corresponds to opposite, so if the opposite side goes to nothing, then sine also goes to 0. Anyways, little nifty trick there if you have trouble remembering that. So our d temperature with respect to time basically simplifies to 3 times negative a b e to the negative bx times 1 plus cosine omega t goes to a maximum, which means it becomes c, just the c, times 1. Nothing else there really to care about. Alright, now this is why they kept the constants separate, so you could just worry about them at the end. Alright? In this particular situation, we have x equals 0 and x equals 4. So the first one, the derivative of temperature with respect to time at x equals 0 will produce negative 3 times the value of a is also 3 times the value of b is 0.03 times e to the negative 0, which just goes to 1, times 1 plus 0.05. You can plug that into your calculator and you should come out with negative 28.4 degrees Celsius per second. And then if we were to plug in for x equals 4, then we'd actually have to solve this e to the power sort of thing. And that should give you negative 25.1 degrees Celsius per second. And that looks reasonable because with this being negative, with the power being negative, this is going to be 1 over whatever this is. Before it was 1 over 1, so that was the largest it could possibly be. So as x approaches as x leaves 0, this exponent will produce a smaller fraction, which will thus decrease the overall answer, period. Plus it just makes sense, you know. The particle that's just beginning to leave at x equals 0 will change its temperature much, much more quickly than one that's already a little ways out, or quite a ways out. We're talking 4 meters. It's pretty much assimilated with it. Well, maybe not quite, but you know. It's going to be much, much closer to room temperature. So this is another example of the material derivative and how it's used.